Hello everybody, welcome to this new video with me. In this video we're going to try to solve a problem by the name of a star's life. So in this problem, a half solar sized main sequence star is ending its life. By my definition of size is the definition of the radius, so its radius is half of that of the sun's. It has an absolute magnitude of 2.3 and its density follows this function. The density at point R is equal to the density of 0, or the central density of the star, multiplied by 1 minus the cubic root of R over R. Now this small r is the distance from a certain point from the center of the star, and this big R is the entire radius of the star. So we're supposed to find its main sequence lifespan, or how long it has lived as a main sequence star, and its central density. And for part B, we will be using some calculus. We're also given Sun's main sequence lifespan, its radius, its mass, and its absolute magnitude. Right. So to find its main sequence lifespan, so first we would like to compare the magnitudes of the sun and the star using the Poisson relation right here, you see on the screen. So yeah, we find this, and then we can find the ratio of their luminosities, which is 10 to the power of ma minus ms over negative 2.5. Ma is of the star, ms is of the sun. We must remember that for main sequence stars, this luminosity is equal to m to the power of 3.5. Please notice that this m doesn't equal magnitude because it wouldn't make sense. This m right here is for this main sequence characteristic. It means the mass of the star. So we can put the derivation here that lifespan is proportional to the mass to the power of negative 2.5, or another way to put it is proportional to luminosity to the power of negative 5 over 7, and such that we can use the ratio we found earlier. We just have to put them all to the power of negative 5 over 7, and we are also given the constants, the lifespan of the sun, magnitude of the sun, and whatnot, and we get that the lifespan of star A is 1.995 gigayears, or 1.995 billion years old. So nearly 2 billion years ago it was formed. Right. Now for its central density, we use the relation earlier that luminosity is proportional to mass to the power of 3.5. So we use it from our earlier ratio. Yeah. So we just have to 3.5 root it and just multiply it by the mass of the sun. We get 3.811 times 10 to the 30th kilograms. Now notice that mass here, we can split it into many parts because a characteristic of stars is their mass continuum, which is the mass in a certain radius, or rather the density of a certain radius, is the same wherever you go. So you can go north, south, east, west, front or backwards, it'll be the same. So we can use it as we can use some sigma notation to help with that. Or another easier way to do it other than sigma is by using definite integrals. So these definite integrals, like I told you, are going to be the parts of calculus. It'll be the integral from r to 0, which is the distances from the center of the star, multiplied by 4 pi r squared rho r dr, which is basically just the mass continuum, the theory inside stars. So we can just check out all the constants. Notice we've already spread rho r as rho nil multiplied by 1 minus the cubic root of r over the radius. Of course, it'll all be based on r. And after that, we can just multiply the r squared into the function inside, so we can do it easier. And we can, after that, we can just use the power rule. And by using the power rule, we would get that is 4 pi r0 multiplied by, in brackets, r cubic over 3 minus 3r to the power of 10 over 3 divided by 10 radius of to the power of 1/3 cubic root, or another way to say, with the limiting values of radius and 0. So what we'll do is we'll put them all under one denominator, and we can substitute r and 0 in the end, which we've done. Notice that we've substituted 0, so it's going to be 0, such that we can further simplify, such that the mass is equal to 2 pi over 15 multiplied by rho nil multiplied by radius cubic. Alright, so we can just flip this equation over in order to find this rho nil here, which is equal to 15 ma, mass of the star, divided by 2 pi radius cubic, which will give us the value of 2.159 times 10 to the 5 kilograms per meter cubic. You see it's very dense. There's lots of helium inside, which, yeah, it's nearing its end as a main sequence, which just makes sense. So this is all for this video. Hope you enjoyed and learned something new. Thank you.